Convective storms hold an extraordinary surprise. Under just the right conditions, they fire off some of the highest energy light naturally found on Earth, terrestrial gamma-ray flashes, or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs. The flash produces an abrupt reconfiguration of the electric field. In some cases, a surge of electrons rushes toward the upper part of the storm at speeds nearly as fast as light. When deflected by air molecules, these accelerated electrons give off gamma rays, producing a TGF. Data from NASA's Fermi Gamma Ray Space Telescope suggest more than 1,000 TGFs occur each day all over the globe. This adds another important piece to the puzzle of our understanding of TGFs and how they are created in thunderstorms, the most powerful natural particle accelerators on planet Earth.
I'm really interested in the radio waves that come off the lightning. Most of those radio waves are trapped between the charged part of the atmosphere, the ionosphere, and the ground, and that's why when we put up our 60 or so radio receivers around the world, we can detect the lightning, because most of the radio wave is trapped. But a small fraction of that radio wave escapes through the ionosphere into space that surrounds the Earth, and it propagates through the space. And as it propagates, it's changed. It travels along the magnetic field of the Earth back down to the top of the atmosphere in the southern hemisphere, where it spreads out. So if you have a radio receiver in the northern hemisphere, you hear. If you have a radio receiver in the southern hemisphere, you hear what happens to that click after it's traveled through the plasma that surrounds the Earth. Now, the phenomena that occurs when it travels through that plasma is called dispersion. In this case, the high frequencies travel fast and the low frequencies travel slow. So you start off with click, all the frequencies are lined up together. By the time it's traveled for 1 second or so through the plasma surrounding the Earth to get to the ground in the southern hemisphere, instead of being a click, you get. The high frequencies arrive first, the low frequencies arrive slower and slower. It goes from being a spheric to being a whistler, because it sounds like a whistling tone.
Due to its molten iron core, the Earth has a magnetic field around it, just like a bar magnet. This magnetic field extends outwards into space, forming a big bubble that we call the magnetosphere. The inner layer of the magnetosphere, from near the Earth's surface up to 1,000 or so kilometers, is called the ionosphere because it is made up of particles ionized via radiation from the Sun. In low-frequency radio astronomy, when we point our telescopes to the sky to measure the faint signals that travel through space to reach us, we need to take structures and perturbations in the ionosphere into account that might change these signals. We need a good understanding of the effects of the ionosphere to make sense of our data. Pictured near the surface, the Earth's magnetic field lines run parallel and come out at an angle to the ground. It has long been postulated that tubular plasma structures go along the magnetic field lines, and it is structures like these that can affect our astronomical measurements. Previously, people could only guess what they might look like, since no one has ever been able to image them.
Cyclotron radiation is electromagnetic radiation emitted by moving charged particles deflected by a magnetic field. The Lorentz force on the particles acts perpendicular to both the magnetic field lines and the particles' motion through them, creating an acceleration of charged particles that causes them to emit radiation as a result of the acceleration they undergo as they spiral around.
An air shower is an extensive cascade of ionized particles and electromagnetic radiation produced in the atmosphere. When a primary cosmic ray enters the atmosphere, the term cascade means that the incident particle, which could be a proton, a nucleus, an electron, a photon, or a positron, strikes an atom's nucleus in the air so as to produce many energetic hadrons. The unstable hadrons decay in the air speedily into other particles and electromagnetic radiation, which are part of the shower components. The secondary radiation rains down, including X-rays, muons, protons, antiprotons, alpha particles, pions, electrons, positrons, and neutrons. The dose from cosmic radiation is largely from muons, neutrons, and electrons, with a dose rate that varies in different parts of the world and based largely on the geomagnetic field, altitude, and solar cycle. The cosmic radiation dose rate on airplanes is so high that, according to the United Nations UNSCEAR 2000 report, airline flight crew workers receive more dose on average than any other worker, including those in nuclear power plants. Airline crews receive more cosmic rays if they routinely work flight routes that take them close to the North or South Pole, at high altitudes, where this type of radiation is maximal. The air shower was discovered by Bruno Rossi in 1934. By observing the cosmic ray with the detectors placed apart from each other, Rossi recognized that many particles arrive simultaneously at the detectors. This phenomenon is now called an air shower. Thank you for watching. For more educational videos, please subscribe to WizScience on YouTube or visit wizscience.com.
The TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines, and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source, and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays.
Deep within their roiling clouds, thunderstorms hold an elusive surprise. Under just the right conditions, they produce some of the highest energy radiation naturally found on Earth, terrestrial gamma ray flashes, or TGFs for short. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine a TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength and evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator.